We live in a time of global transformation. The Energy Futures podcast explores how we can accelerate the expansion of clean energy technologies and reduce our reliance on fossil fuels. From heating and cooling our homes to moving around our planet and beyond, we bring together researchers, scientists, business leaders, and communicators to exchange knowledge and try to answer one important question. How can we create a sustainable energy future for all? This podcast is produced by Energy Futures Lab of Imperial College London.
What if the future of clean energy isn't on Earth, but orbiting high above it? Today's episode is hosted by Edoardo Taricco, a mechanical engineer graduate of the MSc in Sustainable Energy Futures from Imperial. His guest is Martin Soltau, an entrepreneurial leader with deep expertise and achievement in the aerospace and renewable energy sectors. Martin is the co-founder and co-CEO of Space Solar, a leading startup in the revolutionary sector of space-based solar power. Today, they will be discussing space-based solar power as an era-defining new source of clean energy, the manufacturing, testing, and longevity of satellite technologies, and financing space-based solar power.
Hello, everybody, and welcome back to another episode of the Energy Futures podcast. My name is Edoardo Taricco, and I'm joined by our wonderful guest, Martin Soltau. And today we are discussing the very exciting topic of space-based solar power. And anybody who knows me personally knows that this is something I'm very excited to talk about and have a lot of curiosity around. So very happy for you to join us and take the time out of your schedule. And so Martin is the co-CEO of a company called Space Solar, who is developing space-based solar power technology, and as he can elaborate on. And he's also the UK's space-based solar power advocate and has done some amazing work outside of his company as well. So thanks again for joining us, Martin. And it would be great for you to introduce yourself, your background, why you're really excited by space-based solar power. And also, after that, it would be great for you to, in your own words, describe what space-based solar power is, because I'm sure that a lot of our listeners may not be so aware of what it is.
Well, thanks, Eduardo. Great to be here and on the Energy Futures podcast. As you say, I'm co-founder and co-CEO of Space Solar. My background is really in the aerospace sector all my life, doing future aerospace programs and then latterly leading major programs into the big American primes, Boeing and Lockheed. Then I set up and led the aerospace and space business for a consultancy here in the UK, Fraser Nash. And it was at that time, talking to my energy buddies in Fraser Nash, that I realized how difficult the whole net zero project is, and that the government wasn't really looking at things like space-based solar power in the planning and pathways. And with my aerospace background, I knew about space-based solar power and that it was becoming a bit more viable. Got a good conversation with the government going. I was lucky, I found a physicist in the energy department, Bayes at the time. And the long story cut short is that we were awarded a techno-economic study of space-based solar power, which this is back in 2019, 2020. And that really sought to ask a number of questions. Is it technically viable? Is it economically viable? Could it be delivered in a time to make a difference for net zero? And what would this do for the UK? Would there be good economic benefit for the UK? And the answer to all of those four was very, very positive indeed, far more positive than any of us thought. And that got me going on this journey. I thought, well, this is incredible. So I and a colleague founded something called the Space Energy Initiative, which is a coalition of the willing, bringing together the energy and space sectors, because companies in energy don't really know about space. It's just difficult, and why would you go there? And similarly, the space sector didn't really know about energy. There was no connection there. So that was an important part of it. And having done that, we've got about 100 companies in the Space Energy Initiative. And then we decided we needed to do this. We needed to get investment and actually deliver the program with the strong support of this community. And so we founded Space Solar.
That's extremely interesting, and I'd be really interested for you to talk a little bit more about the market. And as somebody who is, really involved and is a major player, how does your company fit in? So, could you talk about the technology that you're developing, the prototype? If you could talk about the deal with Reykjavik Energy, that would be amazing as well.
So, for your listeners, if I just briefly describe what space-based solar power is. Perhaps we're talking about very large satellites harvesting solar energy in space. Our concept is you have reflectors, solar panels, space-rated solar panels. You convert it into microwave, high-frequency radio waves, and beam that down to Earth-based rectifying antennas. And this is at gigawatt scale typically. And so our technology is the Cassiopeia design. Our chief architect has been working on this for about 15 years. He's gone through a number of iterations. He's a real world leader in space-based solar power. And the important thing, and the challenge, I think, for space-based solar power is twofold. Firstly, the way it works, we'll hopefully talk a little bit more about how it works in the system, but you really want to have baseload, continuous power. As the satellite goes around the orbit, it's got to continuously harvest the energy, and it's got to continuously beam that energy to the ground-based receiver. And this is what we really need for the energy system. It's continuous and also dispatchable power. And our Cassiopeia design has that ability by steering the beam in a solid-state system through 360 degrees with no moving parts. So if you can imagine, it's got two large reflectors either end of a power core, and the reflectors are always pointing at the sun as the satellite goes around the orbit. And so the satellite has to beam the energy through 360 degrees to give this continuous power all the way around the orbit. So that's a really important thing. And secondly, the economics are critical to this. So you have to have a solar power satellite that is light enough that you don't need too many rocket launches, because rocket launches are a key element of the capital cost.
So this Cassiopeia design, how does it compare to other designs? What are other designs that are being developed or proposed or iterated in the space-based solar power sector? How does this one match up? Is this considered to be the best way forward, or what are other alternative designs that are being considered?
Yeah, there's a couple of answers to that. So yes, Cassiopeia really is a market-leading design, and it's not easy to design a solar power satellite that provides this ability to steer, you can continuously harvest the energy, steer the beam without moving parts and with a small design. So a lot of designs are quite large. The key performance metric is the specific power, the amount of power you get out of the rectangle divided by the mass of the solar power satellite. There are designs there which use laser frequencies, typically IR lasers, and there are microwave. And it's a really exciting time at the moment in the space-based solar power world, because a bunch of startup companies have popped up pursuing laser designs. Now they're never going to be baseload, because lasers typically can't go through clouds very well. A little bit, but you lose a huge amount of energy. So they're not all weather, and they're not hundreds of megawatts. You can gang together tens of kilowatts, make up 100 kilowatts perhaps, but it's never going to be in the hundreds of megawatts. Not with foreseeable technology anyway. But they do have applications in defense and niche markets and so forth, because they're much smaller systems. This higher wavelength has higher frequency has much smaller systems. Part of the challenge for space-based solar power, again, is if you're going to have the high utilization for your energy system, you've got to have the satellites up in a high orbit so they can see the sun the whole time. They're not in eclipse as they go around the Earth. And then if they're on a high orbit, like 36,000 kilometers away, the laws of diffraction physics mean that you have to have very large apertures, a transmitting aperture and receiving aperture for a given frequency. We use 5.8 gigahertz because that's one of the industrial scientific medical bands. So it's a band that can be readily used, and it's in that lovely weather window where the beam of energy can go through the atmosphere, go through the weather with almost no loss. So that's what makes it all weather and really valuable. Clearly, laser-based systems can't do that. But the advantage is they're small and our systems are pretty large. So if you then look at the different microwave systems, there's a bunch of interesting designs. Some don't even try to do continuous power beaming. They'll lose power twice in orbit. They're what's called gravity gradient stabilized designs, so they're always looking at the Earth. So twice a day they're edge on to the sun, so they lose the power. So the Japanese have got a design like that. It's still very viable, but it's not quite got the same utility that a truly baseload design has. There are probably 9 or 10 different designs with different characteristics, which is great because it means that the space-based solar power is, you can see that there are different ways to crack the problem, and it makes the whole thing more viable, as a new energy source that's going to come along, and competition is a great thing.
Yeah, that's amazing. So essentially, you get sun rays that come, and the solar panels in orbit harvest the energy and transform it into microwave radiation, which is then beamed to a receiver on Earth, and that beam you tune the frequency such that there's minimal losses in the atmosphere, and then the receiver then does the opposite and turns that microwave radiation back into electricity, which then feeds into the grid.
Yes, exactly. And if I add a few other points about this, so we use microwaves because it's comparatively low energy density, so it can be regulated, it's safe. It's safe for humans, for flora and fauna. It's safe for civil aviation, though we don't have to have keep-out zones. And so that's one thing. It's also mature technology. The components are available to now with the very high efficiency, converting from electricity to microwave and back to electricity. And so, we can get these scale-up pathways. The other interesting challenging thing about space solar power is that because these systems are large, you have to have several rocket launches, so you need to assemble them in space. And they're hypermodular, hundreds of thousands of identical modules, all clipped together, each with the ability to collect and convert and transmit the energy. So they don't depend on each other, but they collectively make up this big transmitting aperture. But it means that we have to assemble these modules in orbit. That's not been done before. We know how to do it. We've done a lot of work there, but it is one of the interesting challenges, engineering development challenges that we've got to address with space-based solar power. But modularity is key because you get the production, high production volumes, and the low unit production costs that come from that. And it also gives this huge resilience. So if you get failures, which you do, space is a harsh environment, then it's really resilient to that, and you get this very graceful pathway. And it also gives you those scale-up pathways, when you're manufacturing these things at scale.
Yeah, it's really interesting because if you break down the space-based solar value chain, as you alluded to, there are so many different components. You need to manufacture and there's the generation technology itself, but then there's the whole aspect of transporting it to space and then assembling it in space, and then there's the receiver. So there are all these different components. what is it that space solar focuses on? So you're developing Cassiopeia, but what advancements have you made in the other parts of the value chain, and what is it that you're most dependent on, and what partnerships are you looking to really build?
Yeah. So space-based solar power doesn't yet exist as an industry. So we're having to develop everything. Essentially, we're developing the solar power satellite, the assembly machines, the power beaming, the rectenna. We're working very closely with Blue Origin and SpaceX in particular on making sure that our roadmaps dovetail with theirs for the space development. But other than that, we're really having to kind of do everything. We're acting as a prime. We've got some great partners, so we're bringing in the sort of real expertise, particularly in space robotics. So we're working very closely with MDA Space in Canada, who are probably the world leaders in robotics. We're working with Imperial College, who have got some great work going on with Professor Paul Mitchison in the Wireless Power Lab, and Professor Goran Sturbeck, who is the Professor of Energy Systems, who's been doing some really fascinating work on how space-based solar power integrates into the energy system. And there are so many other aspects which are beyond the technical, which are needed to make this a thing.
Yeah. It's interesting that you mentioned SpaceX. I came across an old YouTube video of Elon Musk giving a talk at a conference 6 years ago, which you may or may not be familiar with, but he was asked about space-based solar power, and he said, quote, "If anybody should like space-based solar power, it should be me. I have a rocket company and a solar company." And he goes on to not say very positive things about the technology, and this was a long time ago, but his main argument was that when you compare it to ground-based solar, the energy conversions can't yield the same sort of output, and he argues that it's just simply better to deploy a large amount of land-based solar. To what extent his numbers were correct, it is debatable. But as an expert in the field, what is your view on this, and how does it compare? What's the argument for space-based solar power over just a large amount of ground-based solar?
Yeah, we in the industry, so we all know about his views. Actually, I'm told that SpaceX have been studying space-based solar power. I think in that interview he was asked a question and he had to sort of respond off the cuff, because to get the energy system working, you need dispatchability and you need baseload. I think if we can kind of just talk about the energy system for a moment, it's because it's critical to this whole argument of why not just carpet more of the world with terrestrial solar, because it's so cheap, isn't it? And we've got it here today. It doesn't work. It actually makes the whole energy system much more expensive. And okay, this last week we've seen the blackouts in the Iberian Peninsula in Spain and Portugal, which seems to have been caused by the grid stability problem, and intermittent wind and solar certainly don't help. Whether that was the fundamental cause, I don't think we yet know, but it certainly doesn't help not having the base load. So coming back to the work that Imperial have done, the key thing about the energy system is that you need, if you're going to have high percentage of weather-dependent renewables, you need to have that backup sources of dispatchable power, which are sat there, paid for, ready to go, and potentially able to give your whole capacity so we're duplicating our energy systems. You've got huge scale up of the transmission and distribution system to cope with the very low density wind and solar, and typically bringing it from the north of Scotland down to where it's being used here in London and the southeast, for example. And all of this makes the energy system very expensive. You have huge curtailment and constraint payments for when the wind's blowing too much, or whether when the grid physically can't take the energy. So what Professor Sturbeck's analysis showed, he has a very sophisticated whole energy systems model. They put in up to 8 gigawatts of space-based solar power into that model. This is the UK modelling the future energy systems. And the model sucked up as much space-based solar power as it could. It displaced the overbuilding of wind and solar. It reduced the amount of grid transmission that you need. It reduced all the curtailment payments. And then when we were generating nicely with wind, you weren't paying space solar to switch off. That was exporting power to other countries. And the net savings was for 8 gigawatts of space-based solar, had net savings of £4.1 billion per annum for the system. So, it just shows, I think, really graphically why terrestrial solar just doesn't work on its own. It's arguably not great in Northern Europe anyway. Perhaps talk about wind rather than solar, but the same thing applies. So that's the answer to Elon Musk. You need to look at the energy system as a whole. He does have a energy storage company, so maybe he's not totally impartial.
That's a good point. He's battery storage. That's a good point. And so the Fraser Nash consultancy reports that I'm sure you had a big part in, that came out 4 years ago, highlighted a levelized cost of electricity that is quite competitive for space-based solar power of £50 per megawatt hour. How has that evolved? Is that still the most reliable estimate of the cost economically? How does it compare to other baseload power generation sources?
Yeah, so that number came from some good techno-economic modelling done by Fraser Nash, looking at the sort of N-of-a-kind mature system in the sort of 2040 timeframe. Since then, there's been a great deal of work. Space Solar's done about £5 million worth of engineering, design and development and demonstration work. We've really taken the maturity of both our economic modelling and the engineering to the next level. And so our projection is that mature space-based solar power in the 2040 timeframe will be about £25 per megawatt hour. In a bull case, if you get the cost of launch right down, like many industry analysts are suggesting, it could come down to sub $100 per kilogram to low Earth orbit, then the cost of space-based solar power could come down to as little as 10 or 11 pounds per megawatt hour. If you compare that with today's cost of mature wind and solar, so wind has a strike price of £82 a megawatt hour in today's prices. And that's not going down. The industry itself says the next allocation rounds are going to be probably bidding higher than that. So even £50 per megawatt hour for baseload dispatchable is insanely cheap and really exciting. And this is really why the government is excited about this. Nuclear, for comparison, is about 120, but of course they don't factor in all the decommissioning costs of nuclear. So the levelized cost of electricity is maybe something would be good to talk about, because that's a very misleading figure anyway. So it needs to be used with caution.
What are the main risks or uncertainties or bottlenecks that could really stop a space-based solar power system from really going down the cost curve and scaling to the point where the economics really make sense?
Yeah. We've got a development program. We've just finished a big design program, which was funded by Department for Energy Security and the UK Space Agency. So we've got the a really good starting point now. And even with this very non-mass optimized design, we've got economics that look pretty much like offshore wind, about 82 pounds per megawatt hour. So it's looking really good. The things that make the economics work are essentially getting the efficiency of the power beaming right through the energy chain from the sun to the plug. So you want to minimize the losses at each stage. And we've got pretty conservative targets for each of those. And we've got a really clear plan of how we're going to get to our target at the moment. And minimizing the mass, because you've got to launch it. And then other big factors are things like the cost of money. So when you start an infrastructure program like this, you're raising money on the capital markets. The early stage it's venture, hopefully with a bit of government grant, and then you're getting the sort of relatively high cost of capital. But the cost of capital has a big impact and on the levelized cost.
Yeah. And just to build on that, who is financing space-based solar power initiatives? Because this is a technology that has extremely long lead times, very capital intensive. So where has most of your funding come from?
To date, our funding has come from government grants by Department for Energy Security, the UK Space Agency, a little bit from FCFC. So it's government research. We had a couple of £1 million from a Middle Eastern entity, which was great, but just again as just project grants. We've had a little bit of in angel investment as well, which is great, and we're currently raising a seed round, £10 million seed round at the moment, and that's all going to be private sort of venture funding. In other startups, so in America, there's a startup called Etherflux. They're pursuing this laser-based system. They've just raised a $50 million Series A, again from venture. So this is super exciting. So this new this new technology is already moving from curiosity research into being an investment class.
Yeah, that's incredible. So just an additional question I had around the actual solar technology that is used by your Cassiopeia design, because the traditional solar industry is such a big sector in itself that right now is dominated predominantly by silicon, monocrystalline silicon. But there are other emerging technologies like perovskites and multi-junction solar cells and even different chemistries that are really interesting in themselves. How do you, first of all, which specific solar technology or chemistries does Cassiopeia use? And how does the development of these emerging solar technologies relate to the Cassiopeia design, and how close are you looking at these?
Cassiopeia at the moment uses triple junction gallium arsenide photovoltaics with reasonable concentration, about 15x concentration. That's this particular design cycle, which is pretty early in the development, and the economics are looking pretty good at that. There's some really interesting research being done by Southampton and particularly Cambridge and others in this ultra-thin film PV, which is self-annealing in the space environment. So we can't just pick up kind of standard silicon. But it's too low efficiency, degrades very rapidly in a space environment. So the harsh space environment and the efficiency is quite important. And there's a really nice so the nice thing about Cassiopeia is it's a bit agnostic to the type of PV that we use. We can take advantage of new technologies that's coming along. The other thing I think about is the sort of sustainability and environmental point. So use of critical minerals is a really, really hot topic and a really critical point for the sustainability of renewable energy sources. And one of the big advantages of space-based solar power is it uses 2 to 3 orders of magnitude less critical minerals than terrestrial solar for a given quanta of energy. And this is a point that is very much up in our minds as we optimize what PV technology we use. So with concentrated technology, obviously the acreage of PV is much smaller. The 100% utilization, because it's day and night and all weather, you're using it all the time, and that means for for a megawatt of every megawatt hour of any energy, you've got a far smaller area of PV. So it's an interesting trade between the kind of economics and the sustainability as well.
Yeah, that's really interesting. And just going back to the role of and how space-based solar power fits into the energy systems, can you talk a little bit about the receiving end and the rectennas? What do they look like, and how are you planning on even going about fitting that into the grid, or even from a logistics point of view? What does that look like? How much space do these take up? Do they combine with wind, offshore wind? What does that look like?
Yeah, the rectifying antenna or rectenna is like a large mesh. If you imagine the beam coming down from the satellite, you've got to have a contiguous area. And for the big gigawatt scale systems, these are about 5 kilometers in diameter. And if the satellite's up in geostationary above the equator and we're in latitude 52 or something, then you can imagine it forms an ellipse. So the rectenna would be an ellipse with a sort of north-south axis being the long axis. But they're a very sparse, lightweight structure, essentially. It's a mesh on poles, which can be either offshore, integrated next to a wind farm, or they where you have plenty of land, you could put them onshore and they could be dual use with farming, or potentially even over a data center, something like that. For our smaller systems, and this is another advantage of the Cassiopeia architecture, it can use, we can put them in nearer orbits, in medium Earth orbit, so you get physically smaller systems and physically smaller rectennas. They're between 1 and 3 kilometers in diameter. So it still sounds huge, but because it's dual use, because it's very sparse and really a low impact structure, you imagine this sort of mesh on poles which lets the light and rain through. They're about 8% of the area of an equivalent wind farm, offshore wind farm, modern one, and about 30-40% of the area of an equivalent terrestrial solar farm in energy terms. So it's important for the public acceptance of this. A couple of things I'd say. Firstly, safety. These systems are going to be located away from population areas. They're not going to be next to your kind of supermarket in sort of out of town area or something. They'll be offshore in the UK, so that's one thing. And there's no sort of industrial infrastructure in people's backyards, so it's not like fracking or nuclear power stations from that point of view. And the public engagement we've had to date has been really positive in that respect.
Is there one receiving, system for every generation system, or can there be a generation system that targets different receivers in different places of the planet? So essentially shifting the beam to manage to match supply and demand in different parts of the planet. Is that how it works, or does a whole system comprise one receiving system and one generation system?
Yeah, this is the really interesting part of space-based solar power, what makes it so flexible. So it can be a one-to-one system where you can imagine a satellite up in geostationary overhead, a single rectenna beaming continuously to that rectenna. But in practice, it's a many-on-many system. So these systems will be interoperable. And one of the things that we have to do is establish interoperability standards so that somebody else's solar power satellite can beam to our rectenna and vice versa. Because that's, I think, the way we're going to get a vibrant market going in this. It's not going to be just proprietary space solar kind of key, and so I think that's one thing. Because these systems can export energy wirelessly, no fixed interconnectors, this is one of the things that makes them so valuable and so flexible as part of the energy system. So we would very much be building receivers, rectennas in other countries, or other countries would be building the ground infrastructure, and then they can receive power from whoever's operating the satellites. And it'll be interesting to see how this plays out and how the energy companies and infrastructure companies play in the value chain here. And you can imagine the rectenna is like a power station. It's like a nuclear power station or a combined cycle gas turbine power station. What you get out of that is just reliable electricity. And the space system could be operated by a different entity with a contract to provide power into the market, just like the other elements of the energy market operate today. So
that's really interesting. I hadn't actually thought of that. So the receivers could be operated by different people that operate the generators. And then, so from a governance point of view, then how much discussion is there around how to use space-based solar power fairly? Is that a discussion that is being had, or is it perhaps a bit further down the line? But from a governance point of view, how do you even start to regulate this?
Well, regulation and governance is absolutely key, both for safety and making sure that these things are truly sustainable. And you mentioned sort of how do you make sure it's fair? Do you mean by looking at other nations and making sure that they have access to this sort of energy?
Yeah. So how do you make sure that you avoid a situation in which a company relies very much on receiving electricity from space-based solar, but can't because it's being used by another country that also needs to match supply and demand?
I think that sort of thing will be taken care of by the market. But what's really exciting, I think, is when you look at the developing nations who, in many cases, are not building lots of wind and solar because that actually makes their energy systems more expensive and less reliable. They're continuing to build coal-fired power stations and things. They can develop rectennas and receive abundant, affordable, reliable solar power from space. And it really democratizes energy access. So we would be putting in place power purchase agreements, just as any other energy developer does at the moment. So you guarantee access to however many terawatt hours of energy you want and so forth in a commercial contractual agreement. And then you have the opportunity to sell when you're not providing it to them. You can export the energy elsewhere and things. So I think it's a really exciting concept of operations, which will fit into the current energy market quite well, but open up all sorts of new opportunities as well.
Who are the players? Who are the governments who are making the most progress? Because I've been reading about China and Japan and the US. I think the ESA had the Solaris program that was doing research on it as well. Where is space-based solar power really emerging, and where is the most promise?
Yeah, it's really exciting time. There's a lot of new impetus. So China and Japan have been developing this for quite some time, and they're accelerating their efforts. China's got a very long-term technology development and demonstration program. They're planning I believe, to put something pretty substantial in space by 2028, with in-space demonstrations before that. Japan, I was speaking to the Japanese team last month, they are putting their power beaming demonstration in space early next year. It launches. So they're really, really strong policy-led, government-backed research and demonstration programs, which is great. The US are pursuing this very strongly. They've had a long-term involvement in space-based solar power right back from the kind of late 1960s. NASA visited this pretty much every decade, and they're continuing that with predominantly military-based research and demonstration, but the Air Force and Naval Research Labs, DARPA's doing a lot, both on power beaming, next generation photovoltaics, deployable structures, assembly in space, all of these technologies that are coming together. I was talking to the DARPA lead the other day, because their approach is to just develop technology building blocks that might be useful. And our approach at Space Solar and others who are pursuing this commercially is that you've really got to have a capable system concept so that you know what technologies you need and perhaps what you don't. So I think both approaches have their place, but I think you do need a really coherent, well-designed system concept to make sure the economics work for this. So yeah, a lot of interesting things. Solaris is changing direction, so that's going to be more about the underpinning technology, particularly in space robotics. And then there are some other countries who are sort of really doing some really good research. Korea and India's always been very, very interested in space-based solar power. So it's building rapidly.
I'd be really interested to know how these different governments are approaching space solar and how they're developing it. You know, what are the differences between the technology that you're developing at Space Solar versus the one that the Japanese are developing?
The JAXA Japanese concept is a gravity gradient stabilized thing. So you can imagine a flat sandwich panel with the photovoltaics and the RF electronics all integrated. And then on the other side, it's got the transmitting elements. So it's always facing the Earth and transmitting from geostationary. And the advantage is that it's relatively simple as a structure. The disadvantage is that you lose power twice a day, in 6 in the morning and 6 in the evening. So it doesn't provide that base load. Nevertheless, it's going to be a hugely interesting and technically viable concept. Whether it's as economic as ours, I'm not sure. Be interesting to see. The Chinese system, the leading Chinese system, is called MMR SPS. That's, again, be perfectly technically viable. But if you can imagine, it looks a bit more like a traditional satellite. So you've got these very, very large 12-kilometer long solar arrays with a central transmitting RF aperture. And so you've got to have these kilometer scale power management and distribution cables. That makes it very heavy. And they also have to rotate, mechanically rotate the solar panels to track the sun. So you've got to put gigawatts of power over these rotating joints with these huge power management and distribution. They've chosen to, let's say, solve different dragons than we've chosen. And again, the specific power is the key metric. Probably specific energy would be even better metric, actually. And their specific power is quite a bit lower than ours, but about 0.1 megawatts per ton. Cassiopeia is 0.8 megawatts per ton. It makes all the difference to the economics. And then there are some other interesting concepts. So there's a private companies who've got other different designs. Caltech have got an interesting design where they have free flyers. So they have a whole load of tiles that sort of fly in formation in the same orbit. They're not connected. And that has a whole load of other challenges because two spacecraft flying next to each other are not in the same orbit. They're in very slightly different orbits, so they'll drift apart. So they'll need insane amounts of propellant to keep that all going, and risk of collision, and oh my goodness. So again, they've chosen different dragons to slay.
And I think it'd be great to talk a little bit more about Space Solar. So you co-founded the company in 2022, if I'm correct. And what is the progress that you've made up until that point? I've done quite a bit of research, but for our listeners who may not be so familiar, what if we could teleport into your offices or your workstations, what could you show us? What are the main achievements that you're really proud of to date?
Sure. Well, as you came into the office, the first thing you'd see is a bustling office. We've got 10 great engineers, fantastic team. We've got two demonstrators sat in the office at the moment. One is our Harrier power beaming demonstrator, and this has been it's about a 0.5 meter scale build of the central power core of the Cassiopeia solar power satellite design. And this has demonstrated this ability to steer the beam through 360 degrees, and the retrodirective pilot beam, which we perhaps haven't talked about, and it's really validated our computer modeling of the beam forming. So that's a really important engineering tool, and we've actually toured around a little bit with that, which is great. And the other demonstrator that dominates the office is a structural truss builder demonstrator, which we call Alba Truss. And they've all got bird names for some reason, all of the demonstrators in Space Solar. And if you can imagine this huge solar power satellite, our largest one is about 4 kilometers long, 1.4 kilometers in diameter, and it's held together with these large structural trusses made of carbon composite. And you've got to build these truss bays with assembly machines that live on the structure. And so we've designed this assembly machine to do just that. They take the carbon fiber, roll it out of a backpack, and then build up each truss bay. And for Alba Truss, it's a meter by meter by meter each truss bay, and it can build those up. So they're two quite cool. You'd immediately see. I think other things about Space Solar, we've really set it up as an investment grade business. This is going to scale into a very large, major energy infrastructure business. It's going to be a global business. And so we've got a stunning board. We've got some really great partnerships. I mentioned MDA Space, but we're working really closely with UK companies and institutions like Queen's University Belfast, Oxford Space Systems, and many others. We're really privileged to be inducted into the Sustainable Markets Initiative, which is King Charles's organisation, really bringing together the commercial companies working in the sustainability space. It's given us fantastic reach. It's great privilege to be part of that. And then we've just been awarded today. It's been announced we are part of Tech Nation's Future 50. So after this interview, I'm off to number 10 to go and meet the Chancellor and the Prime Minister for a launch event for that, which would be great.
That sounds really exciting, and best of luck for that. What is your day-to-day focus in the company? Because I know you have a co-CEO. What do you really spend your time doing other than very kindly giving up your time for great podcast episodes? But what does your day-to-day look like?
So my co-CEO, Sam Adlin, he's an incredible guy, and he used to be the chief strategy officer at the Satellite Applications Catapult, so he really knows the space sector, and he also has fantastic skills in creating startups, innovation space and things. So we work together really, really complementary way. I think the day-to-day things we're doing, raising funding is probably first and foremost what we've been doing. So we've got some really strong investor interest. Getting government to be strongly supportive, I think, is been a central part of what we've been doing. This is an exciting, disruptive, transformative technology that's going to give huge economic benefit for those countries that adopt it. The UK's got something of a real leadership position in policy terms, and with space solar, I think we're a global leader at the moment, but you've got to keep ahead. So the government's got a really important role, not only to provide funding, but there's a huge return on that investment, but also to make it possible in terms of the regulations and the environment, and just getting it into policy much more firmly, contracts for difference, that sort of thing. So government's got a really important role to play, and we work really closely at all levels of government. This sort of thing's really important, Edoardo. Talking about space solar power, getting it socialised with the public, with the not just the sort of technical and academic communities, is going to be absolutely key to enabling space solar power. Any new technology needs to survive the test in the court of public acceptance, and so having that public dialogue is really important, and it's something we've been doing quite a lot of work on. And then the other really important thing is we've been working our engineering program. So we won a couple of £1 million from government grants, and we've just finished what we called our Cassidy program, which has really advanced the maturity of the solar power satellite. So that's now a concept maturity level 4. The underpinning, we've got really clear design definition of the underpinning subsystems. We know how to build it and what the detailed technologies are for all of the elements of this. It needs a lot more engineering work to, many more design cycles to refine and optimize and get the mass down and so forth. But already, it's at this stage where it would be economically viable, which is really exciting. And there's huge pathways to get it down to the cheapest form of energy.
Could you talk a little bit about your partnership with Reykjavik Energy? Because from what I understand, there's a partnership there where you're going to actually send your technology into space and generate your first electrons for them. Could you talk a little bit about that partnership?
Yeah, they've been great. So you would imagine Iceland has all the energy it needs from geothermal. Why would they want to do? Reykjavik Energy, a very entrepreneurial energy company, and we really value that partnership. We've got a letter of interest from them for a pilot project, hopefully leading to a power purchase agreement. But what we'll be doing when we get our seed funding is to really focus on all of the ground infrastructure, the sites for the rectenna, the permitting and regulations that we're doing. So it's going to pipe clean all of that really important process for making this integrated into the energy system there. And the support of a very capable energy company like Reykjavik Energy is going to be brilliant. I'm seeing them next week.
Yeah. So what is this sort of roadmap? Could you elaborate a little bit more about the roadmap as to when you plan on having real parts sent to space? Could you talk a little bit more about the plan in the next 10 or in the near future?
Yeah, we have essentially a 5-year roadmap to the proof of concept in space, generating and beaming substantial power down to Earth. I mentioned earlier that one of the big challenges for space-based solar power, particularly microwaves, is that these systems end up being very large. And the conundrum hitherto has been that if your first of a kind is like gigawatt scale, it's a super difficult step to take. So our roadmap is within 18 months, We've got high efficiency wireless power beaming terrestrially. We've got some really interesting spin-off applications for that. Within 3 years, we're demonstrating our systems in space, so power beaming and this ability to beam to build the structural truss elements. And then within 5 years, we've got our minimum viable product essentially in a low Earth orbit. We've got a great relationship and conversation going with British Antarctic Survey. So they have insanely expensive power for their polar research stations, and they are being incredibly proactive and helpful, working with us on how space-based solar power would integrate with their operations, and they've got a real focus on decarbonising their operations. It's really difficult because they ship in diesel at the moment. It's unbelievably expensive, and it's very difficult to decarbonise in the harsh polar environment. Then we build from that into from once we've demonstrated all of the technologies in a low Earth orbit, we very quickly go into geosynchronous orbit, so with a large system, because we've then so that's within, hoping 9 years, probably 10 years, we'll have essentially kind of 600 megawatt scale systems delivering really good economics. And I mentioned a key part of the economics is actually the cost of finance, cost of capital. At that stage, you've demonstrated it, de-risked it. Hopefully the cost of capital you can get is coming down pretty rapidly. By that stage, in the mid-2030s, the cost of launch will be order of magnitude lower than this. So that's our key roadmap, which is landing really well with investors.
What is the current state of the discussion that you're having with the UK government? How does the UK government view space-based solar power? Where's the discussion at there?
They've been really supportive. So the Department for Energy Security and Net Zero have been funding a series of research projects under the Space-Based Solar Power Innovation Programme. They've been working incredibly collaboratively with the UK Space Agency, and then the broader regulators, Ofcom, Ofgem, the Space Agency and the Civil Aviation Authority have been working really well on the regulations. I think the challenge at the moment with the Labour government at the moment, and the Secretary of State is very focused on his Clean Power 2030, which is really not looking at any of the technologies just around the corner that could have much more impact. And Clean Power 2030 is about massive scale up of wind and solar and battery storage and trying to get carbon capture going. £240 billion was the projected cost. A big part of that is a huge build out of the grid transmission system and things. These and all to be done in 6 years. It's unbelievably costly. It's very difficult to see how it's deliverable, and it's very difficult to see how it's going to be financeable. And so my message to the Prime Minister later on today is going to be, by investing in innovation and technology development like space-based solar power, you get far more return, both in making our energy system reliable and affordable, and in terms of economic benefit for the UK. I mean, it really hits they've got a number of missions, but their clean energy mission and their economic growth missions are directly helped by space-based solar power.
Martin, I want to thank you again very much for coming onto the podcast. I think it's, as you said earlier, really, really cool to be talking about these innovative and potentially really disruptive technologies that could play a massive part in the UK, but also global energy systems. And it's very inspiring hearing you talk about the technology in a very pragmatic sense as well. And the progress that you're making at Space Solar, even having founded the company relatively recently is really exciting and really makes you look towards the future. So thank you very much for coming, and I wish you all the best.
Thanks very much indeed. It is really exciting. Yeah, great. I'll come back and give you an update in a year's time.
Would love to. Yeah, thanks a lot.
Thank you for tuning in to the Energy Futures podcast. Here at Energy Futures Lab, we are dedicated to addressing global energy challenges through pioneering research, innovation, and advocacy. To learn more about us and the exciting projects we are working on, visit our website and follow us on social media. If you enjoyed this episode, please like and share and subscribe to stay up to date with our latest content. Until next time, stay curious.